LDO offers high-quality 3D printer kits, but now they offer these 3D filaments too. What do you think, which is the best for the Voron parts? ABS, ASA or ASA-CF? Hello, welcome to my tech farm. I have here 3 LDO filament types for the testing. If you're not familiar, LDO is a company who makes those great stepper motors, but they also offer a kit for Voron 3D printer. And if you want to build this very popular DIY 3D printer, some plastic parts you have to print yourself. And usually it has to be made from temperature resistant material like ABS or similar. And probably that's the reason why they started to offer these 3 filament types. So I have here 2 ABS filaments in different colors. These are smaller spools, ASA and ASA-CF reinforced with the carbon fibers. I got these 3 boxes from zen3d.eu. So if you are from Europe, maybe you can visit their website, and if the price is okay for you, then maybe you can order these filaments there. This is not a sponsored video by them, except that I got these filaments for free. But this channel actually has its own sponsor, and that's the Polymaker. First, my overall experience about these 3 filament types. ABS. Great temperature resistant material with fantastic mechanical properties, low creeping. ASA. Very similar specifications like ABS. Additionally, it is a UV resistant material too. ASA-CF. Adding carbon fibers will make the part stiffer. This means it resists better to bending, creeping. Sometimes even the temperature resistance is improved too. But on the other side, the parts will be more brittle. This means they resist less to the impact. Even the filament itself is brittle too sometimes, and with the bigger bending it may break in some Teflon tubes, but I will check this later. And sometimes I notice that the layer adhesion is reduced with added carbon fibers, but all these things will be measured in this video. Let's see some specifications directly from the website. ABS high strength rigidity, easy of processing. It is available in several colors. Interesting, the orange is not here, which I got one spool. ASA, excellent mechanical properties, additionally UV resistant material. It's available in only 2 colors currently, and I got exactly this one. And ASA-CF, again excellent mechanical and physical properties and superior UV capabilities. Let's start with the unboxing. This is ABS, 2 colors, orange and dark teal. 0.25 kg spools. Nice vacuum packaging with some desiccant inside, and on a sticker we have some basic print information, for example the temperature between 220 and 260 degrees Celsius. With the dark teal color I will do that detailed test like with the other 2 ASA filaments. With orange only the layer adhesion test, which is the most important I think in this case. Typical whitening on the surface with the stress, but that's normal for the ABS. Now the only thing which I don't like with these smaller spools, that they cannot go into the AMS units. Maybe I could print some adapter, I'm not sure. ASA in olive green. Very similar whitening on the surface during the stress and bending. On the sticker some print settings like the temperature between 240 and 260 degrees Celsius. ASA-CF in a grey color. Again vacuum packaging desiccant inside, bag is not resealable. On sticker again some print informations, the temperature between 250 and 280 degrees Celsius, so higher than the previous 2. Let's see how brittle is the filament. Okay, this has to be measured. Start angle 20 degrees. Around 115. That's not too brittle. But for locking end of the filament, I'm not reusing these holes, but I'm using the clip. And look how full is this spool. Not too full, but the density of the ASA is smaller compared to the PTG, for example. And sometimes it may fall off from the spool. This is, let's say, on the safety side. Now, Zen3D, the company who sent me this filament, mentioned that they experienced some overextrusion with this CF filament and they suggested me to reduce the flow. I'm not sure, but I will check this. I think the CF is more sensitive to moisture, and in that case it will result some overextrusion, so I will try to print as it is now, and if I will experience some overextrusion, I will dry the filament and reprint the test objects again.
Slicer settings. I'm starting from Bambu Lab ASA-CF profile, but let's see the numbers. 60 chamber temperature, texture PI 90 degrees Celsius, the nozzle temperature 280 as recommended max, and the maximal volumetric speed 12 cubic millimeters per second, and the part cooling I'm changing it between 0 and 25%.
The smell is quite strong. Let's extrude a little bit and then we will see how much oozing we have. Oh. Well, there is no oozing, very minimal, so looks like a dried filament. The printing is at 50% and it looks really nice so far. And looks like the filament was dried. The printing will be finished in 10 minutes. The bed is still 60 degrees Celsius, but I could hear that shrinking pop sound. It's already removable.
Slicer setting. Generic ASA is the start profile, and the number 60 chamber temperature, 100 will be on texture PI, 260 on the nozzle, 12 the maximal flow rate, and the part cooling between 0 and 50%. I'm reducing this one a little bit.
From these three filaments, this is the only one which can go into the AMS unit. This printing will be also very nice, and the smell is not so strong, and finished without any problems. Oops. Adhesion is great, it partly cooled down.
And let's see slicer settings for ABS. Generic ABS is the start profile, but let's see the numbers. 60 chamber temperature, 90 on the bed, the maximal nozzle temperature to 60, 15 will be the maximal flow rate, and the part cooling I'm reducing it a little bit between 0 and 50%. Smaller spool, so I'm using external spool holder. Printing is completely fine, no warping or similar.
From all three, this has the smallest odor. I cannot feel almost anything.
Clip for locking end of the filament, and I like to print this from the ABS. In case I want to dry that filament, I don't have to worry. Orange ABS, and from this I'll print only layer adhesion test objects. And I have 4 to have a similar print speed like with the previous one, where I have 4 vertical test objects. And I can still confirm that the smell is not too strong. I mean, it's the weakest between these three filament types.
Another practical example, a hook for a car seat.
Anything you print for inside the car must be temperature resistant, at least PETG, but ABS is much better.
Do you like it? But she told me that she needs another one here.
Let's measure the shrinking. The design length is 80 millimeters. This is ABS. 79.59. This is very similar to the average ABS. If it would be 79.6, that's half percentage of the shrinking. Very similar is with the ASA and ASA-CF, very accurate, exactly 80 millimeters in this case.
It's time to start the testing, but I must be quiet because this is now the kindergarten.
Tensile test ABS. These are horizontally printed objects. ASA. Smallest cross-section area is 4 by 4 millimeters. ASA-CF. In all three cases, the tensile strength is very similar. Interesting, the weakest is with the ASA-CF. And here I mark the average ABS-ASA without any fibers, and we can see that these all three filaments are a little bit below this line. Layer adhesion test. Vertically printed objects. From the orange I have 4 pieces. And now ASA. And ASA-CF. Here you can see my table rating for this test object, and we can see more or less they are very similar. This is the average line, and ABS, ASA-CF are below this line, but still acceptable, and ASA and ABS orange is in the range of the good layer adhesion, but the standard deviation is quite big if you watch these numbers for the ABS, for example. So more or less they are very similar, around 30 kilograms average, except the ASA-CF, this is noticeably weaker. Shear test, these are printed in horizontal position. Shear test, vertically printed objects. Interesting, in horizontal position, the ABS is the strongest, but usually fibers helps in this test, but if you watch the number, the ASA-CF is the weakest, but of course very close to the regular ASA. Printed in vertical position, here the layer adhesion is important, and of course the ASA-CF was quite weak, and ABS and ASA above the average line. Torsion test, starting with horizontally printed versions, load the 90-degree rotation, and the maximum load. Printed in vertical position, only the brake load is recorded here. Printed in horizontal position, load and 90-degree rotation, strongest is the ABS, and the other two ASAs are a little bit below this average line. Printed in vertical position, ABS ASA very similar, very close to that average line, and ASA-CF is noticeably weaker because of that weaker layer adhesion. Creep test, the deformation under constant load of 1.25 kilograms. 16.23, 17.80, 15.12. Day 5, the last measuring. 17.29, 19.55, 15.78. Removing the load. Their permanent deformation is very similar, but the smallest on the carbon fiber version and biggest on the regular ASA. On this graph we can see the deformation, the distance between two reference surfaces, and we can see biggest deformation on the ASA and smaller on ASA-CF, but the creeping is the difference between 2 days, and that's presented on this second graph, and we can see biggest creeping on the ASA and smaller on the ASA-CF. ABS is closer to ASA-CF, and basically after day 2 this became very minimal. Temperature test in the oven, where I want to record the temperature of the first deformation. M10 nut as a small load. This is speed up time-lapse video, and no big surprises here. At 22 and 99 they started with deformation. I just check how soft they are. They are very soft and flexible at this temperature. These are typical values for the ABS ASA, and as always fibers helps a little bit with temperature resistance, so the ASA-CF is a little bit more heat resistant compared to base materials. 3-point bending test. Distance between supports is 50 mm, and I am placing these loads one by one, and I record the deformation after 1, 30 and 60 seconds. Currently you can see the deformation under 10 kilograms. Where the ASA was the weakest in this test, but with the ABS and ASA-CF, interesting smaller initial deformation we can see with the ASA-CF, but look at this, under 10 kilograms, significantly more deformation, not only the initial, but even after 1 minute under 10 kilograms. Of course you don't want to use the parts under these loads, but it is good to know about it. Another bending test, speed up 4 times. The ASA-CF broke very quickly. I'm following the ISO 178 standard. Distance between supports is 64 mm. Interesting to see this whitening of the surface, very useful, sign of the higher stress. On this picture the graph is the most important, newtons in function of time or deformation. And here you can see the maximum load, bending strength and elastic modulus. The bending strength is calculated from the maximal load, so that's why only this is presented on the graph. It's the same ratio. And interesting to see that ABS performs the best compared to other two materials, especially ASA-CF. Here I expected a bigger value. Elastic modulus shows how stiff is the material because it depends from the deformation too. And here just a little bit small advantage on the ASA-CF side compared to the ABS. And of course the weakest is the ASA. Charpy impact test, supported from two sides. All results side by side. IZOD impact test, hold it vertically. And results for the IZOD test. These are two different types of the test, but very similar ratio we can see here. The toughest is the ABS, as this is very important advantage of this material. The second is ASA, and the most brittle between these three is ASA-CF, but even this is tougher than average PTG without any fibers. Our results one more time: creep test, tensile test, layer adhesion, shear test, horizontal and vertical, bending test, the deformation after 30 seconds, the bending test, deformation under these loads after 1, 30 and 60 seconds, torsion test, horizontal and vertical, impact test, IZOD and Charpy, temperature test, and that second bending test, bending strength and elastic modulus. If the main question was which from these three filaments is best for Voron parts, well, if you don't want to use your printer outside, exposed to the direct sun, in that case the ABS is the best choice. Additionally, it is really tough, impact resistant material and similar. ASA is for different applications. I think primarily if it is outside, let's say, I know, bird house or something like that, in that case UV resistant filament is better choice. About this ASA-CF, theoretically it should be stiffer, but this is one of the weakest fiber reinforced ASA materials I ever tested. Two advantages I can see: it's a little bit stiffer, for example, it resists a little bit better to bending, and it will increase a little bit that temperature resistance. Of course, the dimensional accuracy, maybe that is very important for some users, but otherwise, for example, on that shear test printed in horizontal position, fibers always helps here, but this strength was very similar like regular ASA. These fibers are quite weak according to my experience. If you have some other experience with these filaments, fill us down in the comment section. Huge thanks to the Zen 3D for sending me these filaments for the testing, to Polymaker for sponsoring my channel, and to all my Patreon supporters for their donations. And to all you others, thank you for watching this video until the end, and as always, happy printing!